Let's look at this exercise 1.1.6 about the homology of a graph. So we start with gamma finite graph. So I just write the example here, and understand this example will help us to understand the general situation. With v vertices with integer, e edges, e is integer. So in our case, in this example, I take v equals 4 and e equals 3. So this is graph. This graph has no cycle. Cycle means with no repeat vertices, a path with no repeat vertices, but start from the same origin, same point, and go back to the same point or vertices. For example, like this will be a circle. So our example has no circle. This will have some explanation, or you can read this from homology group. Later we'll see this can be read from each one of related complex. So basically we are going to associate a chain complex to this graph whose homology will concentrate at H0 and H1, and they will tell you some information about the nature, or say they give you some environment about this graph. I should not say environment of this graph. I'll tell you some information about this graph, sorry. Because when you talk about environment, you're talking about the environment under certain isomorphism or homomorphism or certain kind of equivalence relations. Your environment handles equivalence relation, then you see that is an environment at this point. We are not thinking of it as topological group, but okay, and we can say it's something invariant for the topological morphism, which means you can move the position of the vertices, and but does not change the shape of it. You do not break it. Okay, it makes some sense. Okay. So let's see this example. In this example, we are going to associate to this graph a v times e matrices. So we and e are both integers. Here in our case, it's just 4 times 3 matrices. This matrix just remembers the information of each edge, start at this which point and end at which point. Basically, so you just follow how this exercise tells you to write down this incidence matrix. This incidence matrix requires you to put the ig position either 1 or -1 or 0. When do you put it 1? You put it 1 when ej start at vi. For example, in our example, this edge E1 starts at V1, and so V11, and so this 1,1 entry is 1. So let's say another one. So this E2 starts at V3, so it's 3, 2 equals 1. Similarly, write it down, and you got a matrix 4 times 3. And the reason we do this is actually when you applying this matrix to a coordinate, so this is 4 times 3 matrix, you have to multiply by 3 times 1 column vector, and say when your column vector is the coordinate vector of this 3R module with basis E1, E2, E3, and then what happened would be, for example, let's just take E1. E1 corresponds to 1, 0, 0. 1, 0, 0 would tell you exactly, compute this, tells you exactly 1 minus 1, 0, 0, right? Because this is just a linear combination of column vectors of this matrix A. Basically, I use the first component multiplied by the first column, and so give you this. And this if you think of this as a coordinate vector for the free R module generated by vertices, which means thing is that coordinate vector for this free R module of V1, V2, V3, V4, and then this element corresponds to V1 minus V2. And you see E2 mapped to V1 minus V2. That's how this matrix record or remember this graph. If your edge start from V1 to V2, and then this matrix apply on V1 gives you V1 minus V2. This is great, right? This is what we want to remember, the information of this graph. And so let's continue. The question asks you exactly to denote C0, the free R module, on the vertices, and C1, the free R module on the edges, and all the other Cn equals 0, and then the differential is given by, so basically there is only one non-trivial differential, which is this one from C1 to C0. We call it, as given by this exercise, this is called the incidence matrix. Okay, that's the one we just described. And then the question asks you to prove if this graph is connected, which means we can start from V1. There is no V0, so there's some small mistake. What is written here? The exercise, there is no V1. There's no V0. Okay. And there is another mistake. I think this is minus of this. Okay. So let's say it is connected if we can start with V1 and arrive at any other Vj, j greater or equal than 2. Okay, then it is called connected. Geometry grid means you can start with a vertex V1 and arrive at all other vertices through your edges. They're both or equivalent to any two vertices is connected by a path. In this case, prove that H0 of this given homology chain of this given chain complex, H0 equals or isomorphic to R1, which means isomorphic to R. H1 C isomorphic to free R module dimension minus, I would say, minus times V minus C minus 1. In our case, will be 0. So, how is it? So basically, let's first say why H1 is 0 in our case, and then in general, let's say what is H1 telling us why it should have dimension minus V minus C minus 1. So in our case, as I said, you have to understand what is. So H1, you look here, this is degree 1, this is degree 0, right? You look at here, this is degree 1. So you have to look kernel of D1, quotient by image of 0, so it's just kernel of D1. And in our case, the kernel of D1 is 0. Why the kernel of D1 is 0? Because, as we just discussed, that map, basically, let's see another example. Basically, for any path, it is mapped to just addition of corresponding vertices, remembering the orientation. So E1 is mapped to V1 minus V2, E3 is mapped to V2 minus V4, and so altogether it is mapped to V1 minus V4. Okay, so you say that if you have a path which is mapped to 0, which is by definition kernel, it means that you have a circle. For example, if you have a situation like this, you have a circle which is E1 to E2 to E3, this is a circle. And this E1 to E2 to E3 will be mapped to 0 because it's mapped to V1 minus V2, V2 minus V3, V3 minus V1, sum them together give you 0. And so actually the dimension of each one should tell you how many circles are there, right? Just look at the other example here with 2 circles, and in that case this is example vertex 4, edge 5, and that's why I'm going to change the sign, because if it doesn't change the sign, it will be -2. In this case, once you change the sign, you read it is +2. Actually this h0 will be dimension 2 because you got 2 circles, which means in the kernel there is it's generated by e1. I haven't fixed the orientation, just to, for example, this, and e2 plus e3 plus e4. Maybe the sign is not correct. I mean the span of this linear independent one generate the kernel for this case. So general idea, I'm really just giving the general idea. Okay, so the kernel of D1 is actually the number of circles. In our case, it's 0. And let's go back to degree 0. What is the dimension of H0? So it's kernel of 0, which is whole R4. 4 here is just, this number is just V. Yeah, how many vertices there? 4 equals the number 4 equals the number V, number of vertices. Okay, and so you have to talk about what is the image. In this case, I'm saying that it's always dimension 1. The reason is that the image of D1 is always almost every vertex is in almost every vertex is an image of D1 except V1, for example. What I'm saying that you can fix the basis. This is kind of in the hint here. If you fix basis V1, V2 minus V1, V3 minus V1, V4 minus V1, this is the basis. And then you can see that V2 minus V1, V3 minus V1, V4 minus V1 are all in the image of D1 because it is connected. Any two different vertices, there is a path connecting them. But V1 is not. That's why this image of D1 has one less dimension than the dimension of free module generated by all the vertices, which has a dimension V, and so the image of D1 has dimension V minus 1. That's why this is always isomorphic to R. But here, in our example, this is 0, but in general it is asked to prove this as dimension minus V minus E minus 1. This is basically because when, in our case, V minus E equals 1, which means there is one more vertex than edges. It exactly means it is in the situation like this. There is no circle. If you have a graph with no circle and no isolated point, then always there is one more vertex than number of edges. But once you got a circle, the number of edges will increase 1, and the number of vertices doesn't change. In this case, it will have one circle, and the consequence it will have dimension 1. If you have even one more circle, it will increase again the number of edges, but the number of vertices is the same, and you have dimension 2. Summarize will give that the information. Compute will give you dimension V minus E minus 1. Change sign. Okay.